Hello students, in this video we will continue talking about the topic of probability, independent and mutually exclusive events. Independent and mutually exclusive events do not mean the same thing. Two events are independent if the following are true. The probability of A given B is equal to the probability of A. If the probability of B given A is the probability of B, the probability of A and B is equal to the probability of A times the probability of B. Two events A and B are independent if the knowledge that one occurred does not affect the chance the other occurs. For example, the outcomes of two rolls of a fair die are independent events. The outcomes of the first roll does not change the probability of the outcome of the second roll. Another example, tossing a coin. Tossing the coin the first time does not affect the result of tossing it the second time. To show two events are independent, we must show only one of the above conditions. If two events are not independent, then we say that they are dependent. To know more about why we have dependent and independent events, let's talk about sampling with or without replacement. Sampling may be done with replacement or without replacement. With replacement, if each member of a population is replaced after it is picked, then that member has the possibility of being chosen more than once. When the sampling is done with replacement, then events are considered to be independent, meaning the results of the first pick will not change the probability of the second pick. When sampling is done without replacement, each member of the population may be chosen only once. In this case, the probability of the second pick are affected by the result of the first pick. The events are considered to be dependent or not independent in this case. If it is not known whether A and B are independent or dependent, assume they are dependent until you can show otherwise. Let me give you a quick example. If you have a bag of M&Ms, you picked an M&M and you recorded the color and then you put it back, then that is sampling with replacement. If you took the M&M, you recorded the color of the M&M and then you ate it, or you did not put it back in the bag, then you are sampling without replacement. For the first one, the events are considered independent because when you put that color back into the bag, you can easily pick the same M&M that you picked the first time. But in the second one, when we do not replace it, the chances of selecting the same one is impossible. And that affects the total number of the M&Ms that we're picking from. So that's why they are considered dependent events. Here is another example. You have a fair, well-shuffled deck of 52 cards. It consists of 4 suits. The suits are clubs, diamonds, hearts, and spades. These are 13 cards in each suit, consisting of 1 through 10 and the jack and queen and king of that suit. If you are sampling with replacement and you find the probability of a jack, then the probability of a jack, we have 4 of them out of the 52 cards. So that is the probability of picking a jack. Now let's say we are sampling without replacement and we pick the first card and the first card was a king. Given that the first card was a king, what is the probability that we're selecting a jack? Remember, we're not replacing the king back into the deck. So the total number we're selecting from went down to 51. Now the probability of jacks, we still have 4 jacks to pick from, but now we're picking from 51 cards instead of 50 cards. Mutually exclusive events. A and B are mutually exclusive events if they cannot occur at the same time. This means that A and B do not share any outcomes and the probability of A and B is equal to 0. For example, suppose that the sample space is 1 through 10 and A is the event of 1 through 5 and B is the event of 4, 5, 6, 7, 8 and C is the event 7 and 9. A and B is equal to 4 and 5 because 4 and 5 occurs both in A and B. The probability of A and B is 2 out of 10 because we have 2 outcomes in A and B and we have 10 outcomes in the sample space. That is not equal to 0. Therefore, A and B are not mutually exclusive events. A and C do not have any numbers in common, so the probability of A and C is 0 because A and C is an empty set. We don't have any numbers there. So the probability of A and C is equal to 0. Therefore, A and C are mutually exclusive events. Now here is the question. Are mutually exclusive events dependent or independent? Can you answer that question and tell me why? That will be part of your discussion for this week, so be prepared with the answer. Next, we will talk about the basic rules of probability, the multiplication rule, and the addition rule. The multiplication rule, if we have two events, A and B, defined on a sample space, then the probability of A and B is equal to the probability of A times the probability of A given B. Remember that the probability of A given B is equal to the probability of A and B divided by the probability of B. If A and B are independent, then the probability of A and B is equal to the probability of A, and we can say that the probability of A and B is equal to the probability of A times the probability of B. So that is the general rule. But if we have independent events, this will turn into the multiplication of the two probabilities. That's a very important rule that we're going to follow. What I would like you to understand is, and know that you're going to use the multiplication rule. And you have to use the general form of the multiplication rule because sometimes events are not independent. Sometimes they are dependent. So you will need to work with the general rule. The addition rule, if you have two events defined on a sample space, then the probability of A or B is equal to the probability of A plus the probability of B minus the probability of them occurring together. If A and B are mutually exclusive, then the probability of A and B is equal to 0. And then the addition rule turns into the probability of A and B is equal to the probability of A plus the probability of B. What I want you to take away from this is when you see or you hear the word or, you know that you're going to use the addition rule. Make sure you're using the general form of the addition rule because you don't know whether your events are mutually exclusive or not. The last two topics that we're going to talk about are the tree diagrams and the Venn diagrams. Sometimes when the probability problems are complex, it can be helpful to graph the situation. Tree diagrams and Venn diagrams are two tools that can be used to visualize and solve conditional probabilities. The tree diagram is a special type of graph used to determine the outcomes of an experiment. It consists of branches that are labeled with either frequencies or probabilities. Tree diagrams can make some probability problems easier to visualize and solve. Let's look at an example. An urn has 3 red marbles and 8 blue marbles in it. Draw 2 marbles, one at a time, this time without replacement from the urn. Without replacement means that you don't put the first marble back before you select the second marble. Following is a tree diagram for this situation. The branches are labeled with probabilities instead of frequencies. So, because we have 3 red marbles and 8 blue marbles, as you can see here, the probability of selecting a red marble is 3 out of 11. The probability of selecting a blue marble is 8 out of 11. Now, in the second time, we're not going to replace the first one. If we selected red, the first one, then the probability of selecting red the second time will be only 2 out of 10. If we selected red the first time, then the probability of selecting blue will be 8 out of 10. Remember, we did not replace the red marble back. If we selected a blue marble the first time, the second time we're going to, the probability of selecting a red marble is going to be 3 out of 10. If we selected a blue marble the first time, then when we select the second time, the probability of selecting a blue marble is going to be 7 out of 10. Now, the probability of selecting red and red the first time and red the second time is going to be the multiplication of both of them, since we said and. So the probability of selecting the red marble first and the red marble second is going to be the multiplication of the first probability and the second probability. Remember, because we said and, we multiply. The probability of selecting red and blue is going to be the multiplication of those two probabilities. Again, red and blue. So we use multiplication because we said and. The probability of selecting blue and then red is going to be the multiplication of both of them. The probability of selecting blue and the next one is blue is going to be the first one blue and the second one is blue is going to be the multiplication of both of them, which is 56 over 110. So here, because we hear the word and all the time, we're going to multiply these probabilities. So this is how we're going to use tree diagram in order to solve some of the probability questions that we find. A Venn diagram is a picture that represents the outcome of an experiment. In general, it consists of a box that represents the sample space, S, together with circles or ovals inside. The circles or ovals represent events. Let's try this example. If we roll a fair six-sided die and let A be a prime number of dots is rolled, and B is the event of an odd number of dots is rolled, then the event A is going to be 2, 3, and 5, and the event B is going to be 1, 3, and 5. Therefore, A and B is 3 and 5. A or B is 1 through 5. The sample space for rolling a fair die is 1 through 6. Let's draw a Venn diagram to represent this situation. So to represent this situation, we're going to draw a box. In that box, we have event A. And since A and B have 3 and 5, we know that events are not independent. 3 and 5 is the common numbers between them. We have the numbers 2, 3, and 5 in A. So we have 3 and 5 in A. This is A. We're missing 2 here. This is B. We have 3 and 5, and we're missing 1 from here. And then we fill the numbers in the sample space. So we have 1, 2, 3. We still need 4 out in the sample space and 6 out in the sample space. So this is the sample space S. It contains everything 1 through 6. And then the event A has 2, 3, and 5. The event B has 1, 3, and 5. They have 3 and 5 in common. Let's look at another example. 40% of students at a local college belong to a club and 50% work part-time. 5% of the students work part-time and belong to a club. Draw a Venn diagram showing the relationships. Let's see, B, the students belong to a club, and PT, students work part-time. So the small circle is student belong to a club, and the big circle, PT, students work part-time. So to represent that, first we're going to put the 5% of the students who work part-time and belong to a club. That is the part that we're going to represent. Now we know that 40% of the students at a local college belong to a club. So the remaining here will be 40% minus 5%, which is 35%. And then we know that 50% of the students work part-time. So the remaining of the part-time is going to be 50% minus 5%, which is 45%. If a student is selected at random, find the probability that the student belongs to a club. So that is the event C, and that is 40%. The probability that the student works part-time, that is event PT, which is 50%. The probability that the student belongs to a club and works part-time, so the probability that the student belongs to a club and works part-time is 5%. To find the probability that the student belongs to a club, given that the student works part-time, this is a conditional probability. So we know that in conditional probability, the probability of the student belonging to a club, given that the student works part-time, is the probability of the student being at a club and works part-time divided by the probability of student working part-time. In this case, this is equal to the probability the student belongs to a club and works at a part-time, that's 5%, which is this area. So we're going to say 5%, divided by the probability that the student works part-time is given in the question, which is 50%, so divided by 50%, which gives you a 10%, 0.1 or 10%. Now to answer the last one, the probability that the student belongs to a club or works part-time, probability that student belongs to a club or works part-time is the probability that the student works at a club plus the probability that the student works part-time minus the probability that the student belongs to a club and works part-time. This is equal to the probability that students belong to a club is 40% or 0.40 plus the probability that student works part-time is 50% or 0.5 or 0.50 minus the probability of the students belonging to a club and working part-time, which is 5%, 0.05. The answer is going to be 85% or 0.85. Remember that we can represent probabilities as percentages or we can represent them as decimals. It's more comfortable to work with decimals when it comes to questions like that. So you will see me switch between percentages and decimals, but it is valid that you represent them in either way. I hope this video helped. I will see you in a different video with more examples.